This is Unit 4, Nuclear Chemistry. By the end of this presentation, you should be able to answer these three questions. Compare fission and fusion and describe how each relates to the environment. Describe the characteristics of alpha, beta, and gamma radiation in terms of what is released and their symbols and charges, and balance a nuclear equation. Now you will need to have your periodic table to balance nuclear equations, so run get that quick. Alright, reactions occur between particles in the nucleus during a nuclear reaction. Elements are converted to other elements, or an element can be converted to an isotope of that element. Matter is converted to energy, and huge amounts of energy are released during nuclear reactions. So there's a couple types of radioactive decay. The first one is alpha decay, and the symbol for alpha is that, where you get a large unstable nucleus decaying into more smaller nucleus. A lot of the larger elements on the periodic table, like uranium, are very unstable and tend to decay into more stable nuclei. So the first step, the nucleus of an atom splits into two parts, and one of these parts, the alpha particle, goes zooming off into space, and the nucleus that's left behind has an atomic number reduced by 2 and a mass number reduced by 4. So this alpha particle contains 4 particles, and 2 of those are protons. So basically, you're releasing a helium atom, right? This is the mass number, and this is the atomic number. So this is the symbol for an alpha particle. Beta decay. This is the symbol for beta decay. A neutron inside the nucleus of an atom just breaks down and it changes into a proton. It then emits an electron and an antineutrino, which you don't really need to know until you get to physics. Just goes zoom off into space, and the atomic number goes up by 1, and the mass number remains unchanged. So our mass number remains unchanged, our atomic number goes up by 1, and it's an electron. Gamma decay. With gamma decay, you get a high energy atom, which has already undergone either alpha or beta decay, and has released those particles, but then it also wants to release some high energy waves. In the gamma decay, there's no protons or nucleons released, so the element remains the same. But you give off these really high energy waves, and that is how the Incredible Hulk came to be. He was exposed to high radiation. The symbol for gamma decay is a funny looking Y. Then you have electron capture, which is basically the opposite of beta decay. So in electron capture, you get something inside the nucleus breaks down, which causes a proton to become a neutron. It emits a positron and a neutrino, which go zooming off into space. The atomic number goes down by 1, and its mass number remains unchanged. So in beta decay, in electron capture, this is the symbol. Penetrating power. Okay, so alpha, beta, and gamma radiation have different penetrating powers, and alpha particles can be stopped by just a thin sheet of paper. Beta particles can be stopped by a thin piece of wood, but with gamma particles, it's such a high energy, you can only stop it with a sheet of lead. And that's why when y'all get x-rays, they cover you with that little lead dress to protect your other body parts from getting zapped with radiation. Alright, balancing nuclear equations. This is the part where you need your periodic table. So what we're going to do is we're just going to add up our numbers and make sure that they match. So if we have 218 on this side, then we need 214 here, plus this 4 will give us 218. So what plus 2 will give us 84? 82. And since this is the atomic number, look on your periodic table, and the atomic number 82, that's lead. That's it. So this is alpha decay. Now here we've got aluminum being bombarded with an alpha particle. which lets off something and a neutron. This is a symbol for a neutron. Okay. So 27 plus 4 would give me 31, but here I've got a 1 for my mass number over here, so I just need 30. Then 13 plus 2 is 15, and this doesn't change my atomic number, so this would just be 15, and phosphorus has the atomic number of 15. And that's it. You just have to make these add up so that they're balanced. So try these on your own, pause the video, and then come back and check your answers. All right, 206 plus 4, we started with 210 over here for our mass number. 82 plus 2, 84. Palladium has atomic number of 84. Here, carbon underwent beta decay. So 14 plus 0 is 14. 6 minus 1, 5. Nitrogen has atomic number of 5. 43, 43, so my mass number didn't change, but my atomic number went up by 1. Oops. So y'all have to watch me every second. 21, 20 minus 1 will give us 19. Okay. Transmutation. Change of one element to another as a result of bombardment by high energy particles. Okay, so it's just a fancy word of saying we're changing our elements into different elements. Fission, a nuclear reaction that releases energy as a result of splitting a large nuclei into smaller ones. So here we're bombarding a nucleus with a neutron. It splits, and we get this huge energy release. We release more and more neutrons and more fissionable nuclei. And so you get this huge chain reaction. Now we've got we have 2 nuclear power plants in Texas. And I think this is funny. You see this huge monster fish downstream of this nuclear power plant. That's because of the nuclear waste. So when you have fission, it produces a large amount of radioactive isotopes. And some of the isotopes they have long half-lives. That means they decay very slowly. So what we do is we have to bury the waste. We put them in these drums and we bury them in the ground, usually at the storage site. And they have to be kept undisturbed for at least 10,000 years. It's that volatile. Now with fusion, you get the same huge energy release as a result of the union of smaller nuclei to form larger ones. You get a ton of energy, way more than you do with fission. But unfortunately, we have not perfected this technique yet. It's very hard. Even though we've got lots of lighter nuclei available to us, we haven't perfected the technique yet. So this is how stars are made, by fusion. And the only time we can get fusion to work is with bombs. So, alright, this is the end of the presentation. If you still don't understand how to balance nuclear equations, then I would go back to the beginning.